In this PowerPoint, we're going to talk about how to calculate static and kinetic frictions, and we're going to pick up in our class after the kinetic friction inquiry. From our inquiry, we saw that normal force affects the amount of kinetic friction an object has. A lot of people think that weight affects it, but weight, or force of gravity, has no effect whatsoever on how much friction there is. Let me give you a quick example. If I'm in outer space and I increase an object's weight, there still is no friction because there's nothing to have friction on. However, if you're on a surface and you push an object, like let's say a flat surface, and you push an object down on that object harder, the weight for that object remains the same, but the normal force increases. It also becomes increasingly more difficult to pull because friction increases as a result. Here's some sample data that might have been collected relating normal force to kinetic friction. As the normal force goes up, so does the kinetic friction. And we can see from the graph that the two appear proportional to each other. So we can see that kinetic friction, this is supposed to say kinetic friction is proportional to your normal force. We can also then relate this as an equation. The force of friction is equal to some number times the normal force. The question is what is this some number? The sum number on this graph is represented by the slope. So the sum number in this example would be 0.45. What does that slope represent? Okay, well, we can calculate it, right? If we rearrange the equation, the slope is just simply the force of friction divided by the normal force. Let's say this in words, right, to get the meaning of it. What is that slope? It represents how much frictional force you have per every 1 unit of normal force. So for example, in this particular case, for every 1 newton of normal force there was, we got 0.45 newtons of friction. Now the slope value on that previous graph is so important and so meaningful to us that we give it a name. We call it the coefficient of friction. The definition for the coefficient of friction is simply the interpretation of that slope that we just gave, which is the coefficient of friction is defined as the amount of force of friction for each 1 unit of normal force. Again, we can calculate it just like we found the slope. The symbol for coefficient of friction is actually a Greek letter, mu, which looks like a U with a tail on the front end. We can calculate that equation, or that coefficient, if we know the force of friction for a given normal force, and you just divide the two. The units for the coefficient of friction is nothing. It has no units. It's just a ratio between two forces. So it's just a number. It's a ratio. It has no particular units at all. What exactly determines, though, how big the coefficient of friction is? That's a whole nother question. From this graph, you can see we have 3 different relationships. If someone measured with a certain amount of normal force how much friction it had for a wood floor, and then they increased the normal force on the wood floor, and they got that relationship, we'd find this graph. If they did the same thing with the same object on ice, and the same thing for the same object on carpet, they would get the corresponding graphs here. We can see that the slope, which is the coefficient of friction, is dependent upon what type of surface there is. So it looks like the slicker the surface, or the smaller the amount of friction, the smaller the amount of coefficient of friction. That just means that, for example, on ice, you get, let's say 0.1 newtons of friction for every newton of normal force, while on the wood floor you might get something like what we had before, 0.45 newtons of friction for every 1 newton of normal force. The higher the coefficient of friction, it just basically means the rougher the surface. You can often think of the coefficient of friction as just that, a measurement of how rough the surface is. So the equation for kinetic friction can be written as follows. The force of kinetic friction is equal to the coefficient of kinetic friction, so hence we have the mu sub k because it's for kinetic, and times the normal force. Now sometimes we write it this way, where we just write the shorthand script for friction, so F is equal to mu, and we drop the k because we're lazy, and times n, which is normal force. A lot of people like to write it this way in a lot of textbooks, and you'll see me writing it this way a lot on the board because it looks like it spells the word F-U-N, or fun. So we just remember, hey, friction is so fun, yay! And that is one way we try and remember the equation for friction. 2 other things we should think about. Does speed ever affect the amount of kinetic friction? I'm just going to tell you the answer. The answer is no, it has no effect. Once the object is moving, it doesn't matter if you're going slowly, fast, or even if you're speeding up. The amount of friction is the exact same. An easy way to remember that is, look, speed is not in the equation. There is no effect on, the speed has no effect on the amount of frictional force. Same thing with surface area. If you have an object and you take that same amount of mass and you kind of spread it over a larger amount of surface area, you end up getting the exact same amount of overall friction, whether it's spread out or over a smaller amount of area. So for example, with our blocks, if we turned it on its side, it would be the same amount of friction as if we laid it flat. Why is this? Let's take a look at where really friction comes from. So if we have a box that is sitting on a surface and it's static, meaning it's not moving, and I'm pushing on it with a force F. Now, it doesn't move. Why doesn't it move? Because of friction. What exactly is friction, and how does this surface push along itself? I understand how the surface can push up, but how does it push backwards? Well, when you zoom up on a surface, the surface is not necessarily smooth. Even what we think of as a smooth surface does have some sort of texture to it. Even on an atomic level, there is some sort of bumps. Okay? So when you zoom up on an object, there's all kinds of little bumps and ridges, and these ridges, they'll fall into each other. And so really, this is actually just a normal force in and of itself. If object B tries to slide, you can see this portion of the flat surface bumps into this portion of surface A. And they actually have a normal force away at an angle. So it's really, friction is really just a portion of the normal force. It's just you can't really see that surface. It's really a perpendicular force though. So we might draw, for example, a typical free body diagram for a situation like this, where we have this force here, drawn as such, force of gravity down on the block, the table is pushing upwards with the normal force, and there's a force of friction. But you know, really, this force of friction is from the table, and this normal force is also from the table. These two forces are technically from the same object and are technically really one force that is diagonal from the surface, where the component over is the size of friction and the component up is the size of the normal force. And so this force is really just these two added together. However, for convenience, we frequently split up normal force and force of friction, but the two are very closely related. All right, now let's take a look at static friction. So with static friction, static just means not changing. So static friction is only when you push on an object and it's not moving at all. As soon as it's moving, you have now kinetic friction. The two are still just friction. The principles still work the same, but how you calculate how much friction you have is different. Let's take a look. This graph here is a graph of how much friction you have over time. So let's say an object is stationary. At first you're not pushing on it. No friction at time 0. And then slowly you start pushing it a little bit, but it doesn't move. You push it more and 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 more. So this is the static region. And then there comes a point where it starts to move. And once it does, the amount of friction drops down. Now we're going to examine this graph and see exactly what that means at different portions. So let's pick 4 different times to look at. We'll look at this time 1, when we're pushing with a small amount of force. Time 2, when we push more. Time 3, right before it starts to move. And time 4, when it actually starts to move. Let's look at these 4 times individually. We're going to draw a free body diagram for each. So let's say at time 1, we're going to make up a force. Let's say the amount of force we're pushing with is, 1 Newton of force. So I'm pushing with 1 Newton of force. In order to not move, how much friction must there be? Well, the net force has to be 0, so static friction must be 1 Newton as well. Okay, so what about the second example? Well, I'm pushing harder this time. Let's say 2 Newtons of force. In order to not move, how much is friction? Well, 2 Newtons, right? This isn't hard. I don't even need to calculate anything. I just think about it. All right, time 3, right before it's just about to move. It's not moving yet. I'm now pushing with 2.5 Newtons, let's say. Okay, so 2.5 Newtons, right? I push. 2.5 Newtons is still not moving. What is friction? 2.5 Newtons. Nice and easy, right? Well, as soon as I push just slightly more, this is the most it can take, right? Static friction just seems to change and respond to whatever it needs to be. This is what we call a reactionary force. But as soon as I overcome a certain amount, all of a sudden it starts moving. And not only moving, but accelerating forward. So if you surpass that maximum amount that static friction can supply. So if it starts to accelerate forward, okay, well then this amount has to be less than the other one. Or sorry, the push force has to be more than static friction. So static friction is going to be a little bit smaller. How big? Well, it'll be the size of kinetic friction, right? As soon as we get to this portion of the graph, we've now got kinetic friction, and it is now sliding forward, and it'll accelerate. All right, well now let's look and see what happens when we increase the amount of normal force acting on the object. In fact, we're going to double it, just like we did in our inquiry with kinetic friction. Before we saw, because kinetic friction was proportional to normal force, you double the normal force, you double the kinetic friction. Well, let's do the same analysis this time with doubling the normal force and static friction. So at time 1, the object's not moving. I'm still pushing it with 1 Newton of force, but it's now heavier. The force of gravity is larger and the normal force is larger. So how much is friction? Well, it's still not moving. It's still got to be 1 Newton of force. That didn't change. Last time it was 1 Newton of force too, but the normal force was smaller. Let's look at the second instant. Okay, I'm now pushing with 2 newtons of force, right? Okay, so what's friction? It's still not moving. It's still net force of 0. It's better be 2 newtons of force. I now push with more up until I get to the point where I'm barely moving. Now here's where it finally changes. I'm pushing with 5 newtons of force just before it starts to move, and the responding frictional force is, well, still 5 newtons. So the pattern is still there. How do you find static friction? Look, it's just going to be whatever it needs to be to make sure it doesn't move. But what's different now is the maximum amount of friction I'm allowed. Before, I maxed out at 2.5 newtons, and doubling my normal force actually doubled the maximum allowed. So this value up here is now going to be greater. Where before the graph probably only went up to here and then dipped down, now it's going to go up higher and before it dips down. So the max is greater and is related to the normal force. But how much actual friction you have is not. It's really related to your free body diagram. And then, of course, it drops back down, just like it does the previous time. So how do you actually calculate static friction? Well, in short, you don't do any actual calculations. You look at your free body diagram. Remember, static friction is a reactionary force. Kinetic friction is calculated. You actually have to just do the calculation, and that's what it is no matter what. It doesn't matter how fast it's going or what it's doing. It's whatever value you calculate using the equation. Static friction is different. You've got to look at the free body diagram. So in this case, in short, static friction is equal to the amount of leftover force of the that is opposing it, right? So in this case, I've got a total of 8 newtons going one way to the, left, and I've got 2 newtons to the right plus whatever static friction force I got so that it doesn't move, right? So the question is how much static friction force? Let's see here. I need 6 more in order to balance, so it's 6. Now, that's interesting. I didn't even use a calculation, right? I don't need it. I need a free body diagram. That's how we do reactionary forces. However, the maximum static friction does have an actual equation, right? That actually did depend on your normal force. So in a question where it says, or when it wants to know about the maximum static friction, you can calculate it, and it's just like the equation for kinetic friction, except for static, right? And so it says the maximum static friction is equal to the coefficient of the static friction times its normal force. Or in other words, write it out in equation form, just like I said, just like kinetic friction. It's the same exact equation, but this time, instead of just Fs and this being S, this is Fs max, right? You never use this equation unless you need to know the maximum amount of static friction possible. Sometimes people write it this way because they say, hey, look, it's either equal to this or less than the static friction, because this is its maximum, so it can actually be less than that value. So in summary, here are 2 equations we're going to use and that you need to write down and have with you. Okay, so the kinetic friction is equal to the coefficient of kinetic friction times normal force, and the maximum static friction is equal to the coefficient of static friction times normal force. They're the exact same looking equations, and this is why oftentimes we just shorten it to fun, and we just drop the K or the S's because we just remember in what scenario, how we use each one. Now there is one more question we haven't really addressed, and that is this. How is the coefficient of kinetic friction compared to the coefficient of static friction? Are they actually the same value? I've been talking about these two different things, but they could actually be the same value, and in very rare cases they actually are. So let's take a look at this graph one more time and see how these two compare. Well, you'll notice that the maximum static friction force right here is much higher than the kinetic frictional force, right? So in both cases, it's the same object has the same normal force. So if the frictional force, kinetic frictional force, is smaller than the static frictional force, right? When you divide the two, you're going to get a smaller coefficient of kinetic friction. It is important to note that usually the coefficient of kinetic friction is less than the coefficient of static friction. It will never be more, and in very, very rare cases, they're about the same. Okay? Let's take a look at one sample problem, and then we'll be done. So here's an example problem where we say, hey, look, I've got a 10 kilogram box resting on a horizontal tile floor. Someone starts to push that box with 32 newtons of force, and I'm going to tell you that the coefficient of kinetic friction between the tile floor, and the box is 0.21. Notice there's no units because it's just a ratio of forces. And the coefficient of static friction is 0.34. So the question is what is the frictional force? This is really just a question of saying, do you know if you should use kinetic friction or static friction? Because they give you both coefficients. So it's really testing to see, do you know which one to use? So, just like we do with any problem solving, we start with getting context, right? So is it accelerating or is it moving? Well, it doesn't say it's accelerating. It doesn't really say it's moving either. It just says he pushes it. I don't actually know if it's moving. Well, how do you actually know if it's moving? Well, remember that graph where it goes up and up and up and then it drops down? Well, the only way to get it moving is if you actually pass the maximum static frictional force. So I don't even know if I've done that yet. I should probably find that out. So really, I need to know if it's moving. We're going to try and figure that out together. Next, we draw a free body diagram, which I've just done for us, right? We've got our force of gravity, or weight, downwards. We've got our normal force up. We've got a push force forward and a force of friction backwards. Now, I don't know if these two forces are the same, again, because I don't know if it's moving or not. If it isn't moving, they're the same, and if it's moving and accelerating, then they're not. All right, so we've listed our variables here, and we want to try and solve. Now, in order to figure out if it's moving or not, like we just said, I need to first know if the amount of force I'm pushing with, if this 32 newtons of force, is greater than the maximum possible static friction force. Because as this push force gets stronger and stronger, so does this force here. I need to know if it's greater than the maximum static frictional force or not. So let's calculate the maximum static frictional force. Sorry, this should say Fs max. So the maximum static frictional force will equal μs times normal force. So I've got μs, I just need normal force, got to find that. So I know that weight and normal force, so we can create an equation for that, for the net force. So in the vertical direction, the net force is this force minus this force will give me my net force. Because it's not accelerating up or down, I know the net force is 0. I can rearrange this and say, hey, look, normal force equals the weight. I know, and a lot of us know this just by looking at this. So if I know find the weight, I found the normal force. Let's go find the weight. How do I calculate weight? Weight is equal to mass times the gravitational field strength, which on our Earth is 9.81, and we're going to approximate as 10. So I've got G is 10. I know the mass is 10, so I'm going to plug in 10 times 10 is 100, and therefore the normal force is equal to 100 newtons. Okay, so now let's go ahead and solve for the static frictional force and see what that means. Okay, so I know the normal force up is 100 newtons, the weight down is 100 newtons, my push force is 32 newtons. Now I'm putting the forces on the free body diagram because sometimes that makes what's going on a little bit clearer. All right, so I'm going to calculate both the kinetic frictional force and the maximum static frictional force and see what we can conclude from this. Now that I know the normal force, I just need to plug and chug. So kinetic friction turns out to be 21 newtons. The maximum static friction turns out to be 34 newtons. Now the question is what is the amount of frictional force? Well, Did I ever surpass the amount of maximum allowed static frictional force as I was pushing it? I'm only pushing it with 32. This static, it will be static until I overcome the maximum static frictional force. The maximum possible is 34. So how much is friction? A common mistake is students will call this then 34 because it's static. But that's the maximum. If this is 34 and that's 32, this object would go backwards. That makes no sense. So, what is the actual answer? This just tells me if it's static or not. Now I know it's static. The answer is just 32 newtons. That's my answer, which is interesting. It's neither this calculation nor this calculation. That throws a lot of students for a loop. Let's look at an alternate situation. What if, instead of this amount of static frictional force being 0.34, what if it was a smaller amount, let's say 0.30? That would change the maximum static frictional force from being 34 newtons to 30 newtons. So now my push force is greater than the maximum possible static frictional force would be, or could be. So how does that change the situation? Well, since this overcame the force of static friction, that means it's now kinetic, which means I don't even need this at all anymore. This isn't even useful because I've got kinetic friction, and therefore the amount of friction is 21 newtons. Now this is going to be the friction, if it's moving, this is the friction no matter what. Whether it's going fast, slow, medium, doesn't matter. This is the amount of friction.